Okay, in this part we are going to talk about the wave-particle duality. Okay, what is the wave-particle duality? Okay, in 1924, Louis de Broglie, a quantum physicist, had put forward a hypothesis stating that all particles can exhibit wave characteristic. Okay, so when it says exhibit wave characteristic, what does that mean? What does it mean by exhibit wave characteristic? Okay, it means that the particle is able to have diffraction and interference. Okay, we know that diffraction and interference is something that only wave can. These are the characteristics or the phenomena that only belong to wave. So that means if something can have diffraction and interference, so that means that thing is a wave. Okay. So Louis de Broglie said that all particles can exhibit wave characteristics. It's just that, okay, however, it is experimentally difficult to show the wave characteristic of particle with large mass. Okay, but it says that particle with large mass difficult to show the wave characteristic. That means only particle with small mass can show the wave characteristic. Okay. So Louis de Broglie predicted that the wave characteristic can be exhibited by light particle. It says the light particle here means particle that are low mass. Okay, light particle here means particle that are low mass. For example, electron. Okay, the mass we know that the mass of electron is very low. Okay, even much more lower compared to proton and neutron. Okay, so he stated that relationship between momentum of a particle and its wavelength is as follows. Okay, so he says that the relationship between the wavelength and the momentum is inversely proportional. Okay, so how is it that he get this relationship? How is it that he get that electron, which is a particle, have wavelength? Okay. Okay, so the experiment that we can do to get the wavelength of electron is like this. We take a slit with small hole, with two small holes, and then take the electron gun. So this electron gun will shoot electron. Okay, shoot electron towards these two holes. Okay. So, and then at the back, we have a detector that can detect electron. Okay, logically, particle that, which is a particle, okay, particle like electron, okay, electron which is a particle, logically, the electron only can pass through these two holes. So when it passes through these two holes, it will go straight, right or not? So by right, it should only hit the detector at these two locations. Okay, that means we can only, by right now, logically, we should only detect electron here and here in these two regions. But the result of the experiment is we can see an interference pattern. Okay, we can see interference pattern. That means we have regions that have electron. Okay, where got electron, no electron, got electron, no electron, got electron. Okay, no electron, got electron, no electron, got electron. Okay, so we see interference pattern. So if we have interference pattern, that means the electron undergo interference. And how is it that the electron can undergo interference? The electron must undergo diffraction first. Right now. Okay, the electron must be diffracted after pass through this small hole. and then after being diffracted, they interfere with each other and produce the interference pattern. Okay, so since the electron can show diffraction and interference, so that means the electron have wave characteristic. And if it has wave characteristic, that means it must have a wavelength. So how to get the wavelength? Okay, so from this interference pattern, we can get x. If you still remember, x is the distance between consecutive antinodal to antinodal line and nodal to nodal line. Okay? Alright, so and then from here, you can get the distance d, and then this is the distance between the two slits. So from these three variables, we can get the wavelength of the electron is equal to ax over d. Okay, so we put a inside here, x inside here, d inside here, then we can get the wavelength of the electron. So this wavelength of electron or wavelength of any particle, okay, wavelength of any particle, we call the Broglie wavelength. Okay, so this wavelength which belong to particle, we call the Broglie wavelength. Okay, and what Louis de Broglie hypothesized also is that the relationship between the wavelength, between the Broglie wavelength and the momentum of the particle is inversely proportional. So how is it that he can find out this? How is it that he can find out about this? So what he can do is he increase the velocity of the electron. Okay, he find that when the velocity of the electron increase, the wavelength decrease. So the hypothesis that we have is that the momentum, okay, because momentum equals to mass times velocity. So here, if the velocity increase, that means the momentum increase. And we find that when the momentum increase, the wavelength decrease. So he get a graph that look like this. 1 over momentum. Okay, directly proportional. So that means we can get straight line equation. Y equals to mx plus c. Y is the wavelength. M is the gradient, and he found out that the gradient is equal to the Planck constant. Okay, equal to the Planck constant. Planck constant is 6.63 times 10 power by negative 34, which is a very, very small number. Okay. Alright. So this x is 1 over momentum. Okay. C is 0. So we get wavelength equals to Planck constant over the momentum. Okay. So this is how we get this relationship, get this equation. Okay. The greater the momentum of the particle, the shorter the wavelength. Since the value of momentum of the particle can be determined by P equals mv, okay, P is momentum, m is the mass of the particle, v is the velocity of the particle. The following formula can also be obtained. So lambda equals to h over mv. So this h over mv is just from this equation. Okay, from this equation, lambda equals to h over p. And momentum equals to mv, so just substitute only. Okay, just substitute inside. So basically, we can calculate the wavelength if we know the mass and the velocity of the particle. Okay, and we can also calculate the velocity of the particle if we know the mass and the wavelength. Okay, all right. Since the value of h, okay, h is Planck constant, okay, Planck constant is a very small number, 6.63 times 10 power by negative 34, negative 34. So that means 0.0000330, 663. Very, very, very small number. Okay, since the value of Planck constant is very small, particle of large mass will have the Broglie wavelength which are too short to be detected. Therefore, wave characteristic cannot be observed. Okay, so he said that because the value of the Planck constant is very small, okay, this value is very, very small. So if the particle have large mass, that means if this mass is large, what happens is this value, the Broglie wavelength, the value will be very, very small. Okay, the value will be very, very small. So what happens if when the value of the wavelength is very small? It says here that the wave characteristic cannot be observed. So why is it that when the wavelength is very small, the wave characteristic cannot be observed? Okay, I repeat one more time. Why is it that when wavelength is very small, wave characteristic cannot be observed? Okay, so the two wave characteristics that we are talking about is diffraction and interference. Okay, let's talk about diffraction first. How is it that we can see an obvious effect of diffraction? Previously, when we learned about diffraction, we learned that if we want the effect of diffraction to be obvious, the wavelength must be longer than the gap. Okay, longer than the aperture of the gap or the slit or the hole. Okay, this hole. Okay, if the wavelength is longer, then we can get obvious diffraction. If the wavelength is very small, okay, if the wavelength is small, then the effect of diffraction is not obvious. Okay, only spread out a little bit. Okay, the wave only spread out a little bit. Okay, so the effect of diffraction will not be obvious. So you see, if the wavelength is very small, then we cannot observe, or it's very difficult to observe the wave characteristic, which is diffraction. Okay, so now we look at interference. Okay, why is it that when wavelength is small, very difficult to observe interference? Because, okay, you see when you have, okay, you shoot particle in through the hole. Okay, and if the wavelength is very small, what happens? From the equation lambda equals to ax over d. If the wavelength is small, that means this value of x will also be very small. Okay, the value of x will also be very small. So what happens when value of x is very small? When value of x is very small, what happens is, you see x is here to here, x right or not. If x is small, what happens is these two fringes, they will group together. Okay, they will overlap each other. So in the end, what happens is you will see all group together. Okay, for example, this one and this one. The x very small, so they will group together. This one group together because x very small. Okay, x very small, all group together. Okay, x very small, all group together. all group together. So in the end, you only see like there is no interference pattern lah. Okay, in the end, you cannot observe interference pattern. You only see two lines. Okay, get the idea. Okay, so again, when if the wavelength is small, if the de Broglie wavelength of the particle is small, then it is very difficult or cannot observe the wave characteristic, which is diffraction and interference. Okay, continue. Okay, in 1927, the presence of wave property of electron was confirmed through electron diffraction experiment. Photograph 7.2 show the diffraction pattern of electron through a thin layer of graphite. This pattern resembles the light diffraction pattern through an aperture as shown in photograph 7.3. So this confirms de Broglie's hypothesis. So you see, first this is diffraction pattern of red laser light. So you can see the diffraction pattern got bright, dark, bright, dark, bright, dark, bright, dark. And then now you look at the diffraction pattern of electron. Okay, diffraction pattern of electron. Also got bright, dark, bright, dark, bright, dark, bright, dark. Okay, got bright and dark there. So this shows that the electron undergo diffraction. Okay, undergo diffraction. So this confirm de Broglie's hypothesis that all particles can show a wave particle duality. That means a particle can show characteristic of particle and also can show characteristic of wave. Okay, next. The Broglie wavelength of an electron beam is approximately 1000 to 10,000 times shorter compared to wavelength of light. This property is very important for higher magnification of electron microscope. Okay, so a comparison between image produced by an optical microscope and an electron microscope is shown in photograph 7.4. So here, this is image of red blood cell under optical microscope. This one is under electron microscope. So you can see using optical microscope, there is a maximum magnification. You cannot see any bigger than that. But under electron microscope, you can have a larger, much larger magnification. Okay, so why is it like that? Why is it that using light you cannot have a very big magnification, but using electron you can have a big magnification? Okay, so the reason why is it that using visible light we cannot have a very big magnification, while using electron we can have a very big magnification? Okay, so we have to understand how is it that we can see an object, for example red blood cell. Okay, so how is it that we can see the red blood cell? We must have light reflect from the red blood cell, then only we can see, right? But because the wavelength of the light is quite big, what happens is only a small part of the light is being reflected, while a lot of the light can diffract and pass through, just pass over the small object, which is the red blood cell. So if that is the case, that means you cannot see the red blood cell in very high detail. That means that small detail of the red blood cell you cannot see clearly. So this means that you cannot have a very big magnification. Okay, but for electron microscope, okay, electron microscope can have a very big magnification because electron have a very small wavelength. So that means a lot of the electron can reflect. Okay, can reflect from the red blood cell. Okay, actually not into our eyes but into a detector. So the detector which is connected to the computer will be able to analyze the reflected electron, and the computer can produce an image of a higher magnification of the red blood cell. Remember, this is due to the small wavelength of the electron. Small wavelength, it can reflect. Okay, it can reflect from small object. Long wavelength, it will be able to diffract, pass through the small object, and only small amount can be reflected. Okay, so this is the same concept like in sonar. Okay, sonar. If you still remember, sonar is a device where you use, where the ship, the ship use the sonar to look for object under the sea. Okay, the sonar where the ship use sound wave. Okay, use sound wave. So, for example, the ship want to look for fish. Small fish. Okay, fish that is smaller. So they have to use sound wave of short wavelength. Okay, the wavelength of the sound wave must be short. Then only it can be reflected by the fish and can be detected. Okay, if the wavelength is long, then it will diffract and just pass through. Okay, it will just pass through, diffract and pass through the small fish. So cannot be detected lah. So the small fish cannot detect because the wave did not reflect from the small object. Okay, so how to get the small wavelength? Okay, how to get small wavelength? The frequency must be high lah. That means the frequency of the sound wave must be high. So that is why for sonar we use ultrasonic wave. Okay, ultrasonic sound wave. Understand? We use ultrasonic sound wave where the frequency is higher than 20,000 hertz. Okay, actually it's not. Actually, the frequency of ultrasonic wave can go until a few 100,000 hertz. Okay, then the wavelength can be very small. Okay. Okay, electrons are said to have wave-particle duality. Okay, electrons are said to have wave-particle duality because they exhibit the property of both particle and wave. So electron, we know electron have mass. Okay, so that means electron is definitely a particle. But electron also can show wave characteristics. So that means electron also have wave characteristic lah, okay, because electron can diffract, also can have interference. Okay, so this is why we say that electron have wave particle duality. Okay, next. Okay, light also possess both wave and particle property. Therefore, light and electron are said to have wave-particle duality. This duality is also found in all kinds of radiation in the electromagnetic wave spectrum as well. Okay, as in subatomic particle like proton and neutron. Okay, so all of the electromagnetic wave also have wave-particle duality. So why is it that we say electromagnetic wave or light wave also have wave particle duality? Okay, we know that electromagnetic wave is a wave, but how is it that electromagnetic wave how is it we know that it's a wave? So how is it that what is the characteristic of electromagnetic wave that show it has behavior of a particle? Okay, we can see from the energy. Okay, we know that the energy of the light, energy of electromagnetic wave is transferred in small packet, which we call photon. Okay, when light shine down, okay, the light energy is transferred in small packet called photon. And we know that energy have mass from previous chapter, E equal mc squared. So we know that energy have mass. Okay, so since energy have mass, that means photon must have mass also lah. And if it has mass, that means it has momentum. Okay, so this is already proven lah. Okay, this where photon have mass and have momentum, this is already proven. And one of the way that they want to apply this is in space travel. So they use the space probe. Okay, they launch a space probe to space, and when in space, it will be able to open up a reflector. Okay, a thin reflector sheet. So when the light from the sun hit the reflector, the light will reflect, right now. Okay, the light will be reflected, and when it's reflected, remember, light, the photon have mass. So that means when it collide with the reflector, the momentum of the photon will change. That means we have a change in momentum. And when we have change in momentum, that means a force will be produced onto the reflector. So it can push the reflector and give it acceleration. Okay, so this is called the solar sail. Okay, solar sail. You can go Google and look more about it. Okay, here is just repeat what previously we already know. Okay, so this E is the energy that is contained within the photon. Okay, photon energy. Okay, the energy inside the photon is directly proportional with the frequency. Okay, frequency of the light. So that means if the light have low frequency, for example, red color light. Okay, red color light, the wavelength is longer, the frequency is lower. Okay, how you know that the wavelength is longer? You just look at the electromagnetic spectrum. You will see that the red color light is near the infrared, and infrared have longer wavelength. Compared to blue light, the wavelength is shorter. As you can see from the electromagnetic spectrum, the wavelength, the blue light is near the ultraviolet, so the wavelength is shorter. Okay, shorter wavelength, and the frequency will be higher. So from this relationship, the photon energy directly proportional with the frequency of the light. So that means this red color light photon, okay, the photon of the red light will have lower energy, while the photon of the blue light will have higher energy. Okay, and we can substitute the frequency with speed of light over wavelength, and we can get this equation. So it's like this. So from this equation, frequency, we can get frequency from the wave equation. V equals to F lambda. This V is the speed of light. F is the frequency of the light. This is wavelength of the light. So this is speed of light. So that means we can substitute this V with C because the small c is the symbol for speed of light. Okay, C equals to F lambda. So frequency equals to C over lambda. So just substitute this inside here, and then we can get hc over lambda. Okay, get this equation. So basically, this just means that if the question doesn't give us frequency but give us the wavelength, we can use the wavelength to calculate the energy of the photon also. Okay, but it's not so important because as long as you know the wave equation, if they give you the frequency, you can use the frequency with the using the wave equation. You can calculate the wavelength also. After calculate, sorry. If the question give you wavelength, doesn't give you frequency, you can put the wavelength in the wave equation and calculate the frequency, and then the frequency put inside this equation, then you can calculate the energy of the photon also. Okay, next, problem solving for photon energy and power. Okay, so the energy of one photon is equal to hf, assuming that n photons are being emitted per second. Okay, this is n. This is what n represents. N is number of photon emitted per second. Okay, that means one second, how many photon is emitted. So that means if every 1 second, okay, if 1 second, 1 photon emitted, so n will be equal to 1 per 1 second. Okay, that means 1 photon in 1 second. Okay, 1 per second. So 1 per second. Okay, so 1 per second. If the value of n is 1 per second, that means every 1 second emit 1 photon. Okay, and of course, if 5 okay, if 1 second 5 photon, so that means n is 5 photon per second. That means per 1 second. So it will be 5 per second, like this. Okay, 5 per second. So it will mean that every 1 second, 5 photon is emitted. Okay, now, then photon power P, okay, P represent the power of the photon. That means every 1 second, the photon can transfer how much energy lah. Okay, basically that's what it is. Okay, so photon power, which is the total energy transfer per second. Okay, total energy transfer per second is P equals to NHF and also equals to NHC over lambda. Okay, so how to get this equation? So from the equation of power, okay, power is energy or work lah. Okay, energy or work over time. Okay, so this E is the energy of the photon. So energy of photon is Hf. Okay, so over T. Now, we separate this per time, Hf. So we can see that this 1 per time, okay, this per time, this can be substituted with n, because n is number of photon per 1 second. Okay, number of photon per 1 second. So how much time? Okay, how much time? How much energy? If 1 photon, then 1 times this is the amount of energy of 1 photon divided by the amount of time that that 1 photon come out lah. Okay, the time it takes for the 1 photon is produced. Okay, so that means like this. So this 1 over T can be substituted with n lah. So it becomes NHF. Okay, become NHF, and then power equals NHF, F is frequency, so again C equals to F lambda, so F equals to C over lambda. Substitute inside, then we get P equals to NHC over lambda. Okay, so this is how these equation are obtained. Okay, this is how we obtain these equations. Okay, okay, let's try the example. Okay, so a 50-watt lamp emit red light with a wavelength of 7 times 10 power by negative 7 meter. What is the number of photon emitted per second? That means they want us to calculate the value of n. Okay, they want us to calculate the value of n. Okay, so from the equation P equals to NHF, okay, but they give us wavelength, so we can convert this into NHC over lambda. Then we can get that, okay, so the power is 50 watt. N is the one that we are looking for, so this H is Planck constant, 6.63 times 10 power by negative 34. And then this is the speed of light, 3 times 10 power by 8, and divide by 7 times 10 power by negative 7. So we will be able to get n equal to 1.7597 times 10 power by 20 per second. So it means every 1 second, this is the number of photon that is emitted by 50-watt lamp. Next, a red laser pen emit light with a wavelength of 670 nanometer. If the number of photon emitted is 3.37 times 10 power by 18 per second, what is the output power of the laser pen? So now they want us to calculate the power is how much. Okay, so again, the wavelength is given up, so that means we straight away use P equals to NHC over lambda. Okay, so the number of photon emitted is 3.37 times 10 power by 18 per second. H is Planck constant, 6.63 times 10 power by negative 34. Speed of light, 3 times 10 power by 8. And then the wavelength. Okay, 670 times 10 power by negative 9. Okay, because it's nano, negative 9. Okay, so we can get 1 watt lah. Okay, 1 watt. Okay, actually 1.0004. Okay, round off 1 watt lah. Okay, number 3, assuming that 10% of the output power of 100-watt bulb is used to emit 2.92 times 10 power by 19 photon per second. What is the average wavelength of the light? Okay, in nanometer. Okay, what is the wavelength in nanometer? Okay, so again, they want us to find the wavelength. So power is NHC over lambda. Okay, so it says that the power is the 10% of the output power is used to emit photon. So 10% of 100 watt. That means okay, 10% of 100 watt. That means is 10 watt lah. Okay, but we show okay, 10 per 100. This is 10%. Okay, times 100 watt. Okay, so n is the number of photon per second. So 2.92 times 10 power by 19. Okay, h is the Planck constant, 6.63 times 10 power by negative 34. Speed of light, 3 times 10 power by 8. And then the wavelength is the one that we are looking for. So because they want the wavelength in nanometer, so we put nano here lah, okay, lambda times 10 power by negative 9 lah, okay, because 10 power by negative 9 is nano. Okay, so later we can straight away get in nanometer lah. Okay, so the wavelength will be 580.788 nanometer. Okay. Okay, so this is it for 7.1 quantum theory of light.